So, quick note on where we were. Last video, DNS turned the name you typed, example.com, into an actual address, a number your computer can connect to, like 192.0.2.10. So now we know exactly which machine on the internet we want. So the browser just asks for the page now, right? Sends off the request, gets the website back. That is what I assumed for the longest time. But no. If the browser fires off that request right now over HTTPS, it does not go anywhere because having the address is not the same thing as having a conversation. Knowing someone's house number is not the same as them opening the door, and definitely not the same as them proving they actually are who you came to see. So, before a single byte of the real page moves, two things have to happen, and these two things are the whole video. 1. We open an actual pipe between the two machines, so bytes can move back and forth without getting lost. And 2. We make the pipe trustworthy. Prove the server really is example.com and set up a shared secret so nobody in the middle can read what we send. A pipe and then trust. And those two jobs have names you have seen, TCP and TLS. And that is all the S in HTTPS really is. Plain HTTP. Send through those two first. So it is not really a different protocol. It is the same request you already know, just made trustworthy before it goes out. So let us build it step by step. And by the end, the padlock is going to mean something very specific. Honestly, kind of different from what most people think. Okay, before we build it, let us get the shape in our heads because it is simpler than it sounds. HTTPS is really just four jobs stacked, each one sitting on the one below it. At the bottom is the address, the number DNS gave us. That is just where the machine is. On top of that sits TCP. Its one job is to open a reliable pipe, so bytes actually get across in order. On top of TCP sits TLS. Its job is trust. Is this really the right server? And can we make it private? And only on top of all of that sits HTTP, the actual ask. Give me the checkpoint page. So TCP is the pipe, TLS is the trust, HTTP is the ask. That is the whole map. And these two in the middle, TCP and TLS, are the part we actually care about here because they happen before your request every single time and almost nobody looks at them. And here is the one thing that tripped me up. So let us kill it now. TLS does not go first. You would think the security comes first, right? But no. In the classic web path, TCP goes first and opens the pipe. Then TLS uses that pipe to set up the trust. Pipe first, then trust. Always that order. So let us start at the bottom of the pipe. So, two machines that have never spoken. Think about it. They have not exchanged a single byte yet. So, how do they open a connection? There is this little three-step thing at the very start called the handshake. Our browser sends one tiny message that says, "Hey, I want to open a connection and I'm starting my byte count here." This first message is called a SYN, SYN. The server sends one stride back. Got it, I had you. And I want to open too. Here is where my count starts. That is a SYN plus acknowledgement and ACK. And then the browser sends one last great, I had you as well. We are on. And that is it. Three small messages and the pipe is open. To reach the server, by the way, the browser knocks on a specific door, port 443, the standard door number for HTTPS. DNS gave us the building, 443 is the door. And you might think, 3, why not 2? I say hi, you say hi back. At high level, when the server answers, I know it heard me, but it does not know that I can hear it. So that third little message is what tells it that mutual yes, I can hear you needs 3, not 2. Okay, the pipe is open. So what did we actually get out of it? Here is the useful part. It is a reliable in order pipe. Let us say the browser sends a bunch of data and one piece goes missing on the way, which happens constantly on a real network. TCP notices asks for that piece again, and holds everything until it can hand the other side one clean stream of bytes in the right order. So up top, the app never sees the mess. No lost pieces, nothing out of order. It just gets one clean stream, start to finish. That is the whole point of TCP. It hides all the mess underneath and just gives you a clean pipe. But, and this is why we are not done, TCP does not know or care what those bytes are. It does not know it is carrying a website, and it does nothing to hide them. Right now, anyone on the network between you and the server, the cafe Wi Fi, your internet provider, whoever, can just read every byte in that pipe, all of it, could even change it. So, a handshake did not make it safer. TCP gives us reliability, it does not give us privacy, and it does not prove who is on the other end. TCP is the pipe, it is not the trust. And that is exactly the job of the next layer. Alright, we have a working pipe, but it is wide open. So TLS steps back to lock it down. TLS, Transport Layer Security, is the real name of this trust layer. The thing that Padlock stands for. Quick aside, you will still hear people say SSL or SSL certificate. That is just the old name. Today it is TLS. The name just stuck. And it kicks off with a browser introducing itself. The first message is literally called the client hello, and it is really just the browser telling the server a few things upfront. It says, here is the TLS version I want, TLS 1.3, the modern one. We will go on with that. Here are the encryption methods I know. And then a really interesting one. It says the name of the site it is trying to reach, example.com. And you might go, wait, why? DNS already found the address. Did we not sort the name already? Here is the thing, one single server at one address very often hosts lots of different websites. So when the browser turns up, the server does not know which of its sites you are here for. So the browser has to say the name out loud. So the server can pull up the right identity papers. One address can be many sites. So we still say the name. It slips in one more thing. It's half of a key. And just hold that thought because the key part is the important one. And it gets its own section in a minute. The server writes back, the server hello, and picks from the menu. Ep, TLS 1.3, and here is my half of the key. So at high level, the browser proposes, the server chooses. But proposing and choosing is the easy part. Anyone can claim to be example.com. So the real question is the next one. How does the browser actually know this server is who it says it is? So this is the heart of the whole thing. Trust. The server says I'm example.com. How does your browser actually check that instead of taking its word for it? Because if it just believed whoever answered, then anyone who managed to sit in the middle could say, yeah, that's me. And you would never know. So the server has to show a certificate, basically a signed ID card for the domain. Let us look at what is on it. The domain name example.com, some dates it is valid between. The server's public key, think of that as one half of a lock, where the matching half stays secret with the server. Hold that, we will use it in the next section. And crucially, a signature from a certificate authority. A certificate authority, a CA, is just an outside organization whose whole job is to issue and sign these ID cards. Think of it like a passport office. You trust a passport because of the office that issued it, not the person holding it. And your browser already trusts a set of these CAs. So the certificate is really the CA vouching, I checked, and this key genuinely belongs to example.com. And the browser runs two quick checks. First, does the name match? The certificate says example.com, and this is exactly who I was trying to reach. Good. But if I had gone to my bank and the certificate came back with some random other name, stop. Big warning. Do not go further. Second, is this signature from someone I actually trust? Your browser and operating system ship with a built-in list of trusted CAs, a trusted store. This CA is on the list, so the browser believes it. If the ID card is signed by someone it has never heard of, it stops. And notice how the job split here. Last video, DNS told us where to go, the address, but DNS did not and cannot prove who is actually there. That is this. DNS finds the address, the certificate proves the name. Two completely different jobs. But here is the correction that really matters. So think about it properly for a second. A certificate proves the name. It does not prove the site is good. All it says is this key really belongs to this domain. A scam site, a phishing page, it can go get a perfectly valid certificate for its own scam domain and show you a real, genuine padlock. So the padlock was never a promise that a site is honest. It only ever promised one thing. You are really taking to the name in the address bar. Much smaller, much more specific than most people think. Okay, here is the part that genuinely tripped me up. So let us slow right now. In a minute, both sides are going to end up sharing one secret key. And that key never once crossed the network, which sounds impossible, right? They are shouting across an open pipe that anyone can read. So how do they both end up with same secret without ever sending it? Because the moment you send a secret across, it is not a secret anymore. And the trick is honestly pretty simple. Once you see it, think of mixing paint. Each side has a private color it keeps to itself and never shares. And each side has a public color it is happy to shout across the pipe. Now, the browser mixes its own private color with the server's public color, and the server mixes its private color with the browser's public color. And here is the whole thing. Because of the math underneath, those two mixes come out to the exact same color. The same shared secret. Both sides now have it. This trick has a name, Diffie-Hellman. But you do not need the math, just the shape. Public halves cross, private halves stay home. And the eavesdropper on the pipe, all they ever saw across were the two public colors. And you cannot get back to shade secret from just the public halves. You would need a private color, and those never left home. So the secret was never sent. Both sides arrived at it separately at the same moment. The key is not sent, it is arrived at. One more quick thing closes a real hole. What stops an imposter from just copying someone's certificate and waving it around? So the server signs a little slip of the conversation with its matching private key, the one only the server has. The browser checks it against the public key in the certificate, and if it lines up, the server has proven it genuinely holds the key. It is not just showing an ID card, it is proving the ID card is its. Then both sides send a finished message. We saw the same conversation and we built the same key. We are good. And now the pipe becomes a real encrypted tunnel. And notice the certificate's key proved identity. It is not the key that scrambles your page. That is this fresh shared one. And it locks and unlocks the same way both ends. This is what symmetric means. The same key both ways. And it is fast. And that get request stuck at the closed gate since the very start of the video, it finally goes inside the tunnel. Safe. So the tunnel is up, the request is flowing. What does that padlock actually protect? Worth being precise here, because this is exactly where people overtrust it. Inside the tunnel, everything is scrambled. The exact page you asked for, your cookies, your passwords, the reply that comes back, someone watching the network just sees gibberish. But some things still leak because they sit on the outside of the tunnel. Whoever is watching can still see the address you connected to, roughly when and roughly how much data moved. So they may have no idea what you read on the site, but they can often tell that you went there. The padlock hides what you do, it does not make you invisible. And none of this is free. It costs a little time. The TCP handshake is one round trip over and back. The TLS setup in modern TLS 1.3 is basically one more. So before your real request even goes, you have spent about two round trips just setting up, which sounds like a lot. But two things. One, this happens once per connection, not once per image. The browser keeps the tunnel open and reuses it for everything else on the page. And two, The second time you visit, the browser and server actually remember each other and skip most of the ceremony. The browser shows a little ticket from last time and they resume much faster. So the first visit pays the full setup, after that it is cheap. Okay, the main story is basically done. Pipe, trust, tunnel, request, one lost honest footnote before we wrap, because somebody is definitely thinking it. I showed you TCP first, then TLS tagged on top. That is the classic path, and genuinely the clearest way to see the two jobs. But a lot of modern traffic actually uses a newer thing called HTTP3, which does not stack them like this. It uses a transport called QUIC that does the pipe and the truss together in one combined step over a different base underneath called UDP. But this is the point, the jobs are exactly the same. Reach the server, prove the server, agree a shared key, then send HTTP or HTTP3. Just does them together and faster. It changed the plumbing, not the idea. So everything you just learned still holds. Okay, let us pull all the way back out. The whole thing comes down to three words: connect. TCP opened a reliable pipe to the address. Three little messages and bytes can flow. But a wide open pipe, verify. The server showed a certificate proving it is really the name you wanted, checked against authorities your browser already trusts, and encrypt. Both sides mix a public half and a private half. Arrived at the same secret key without ever sending it. And only then did your real request go. Sealed inside the tunnel, connect, verify, encrypt. So, the padlock. We started out thinking of it as a little sticker on the page that means this site is safe. Let that go. It is not a sticker, and it is not really about the page at all. It is the receipt for the whole negotiation that happened before the page was ever requested. A pipe opened, an identity proven, a secret agreed. It does not tell you the site is good. It tells you the connection is private and you are really talking to the name you typed. And honestly, that pattern is bigger than HTTPS. Set up a reliable channel, prove who is on the other end, then agree on a shared secret. That is how almost every secure conversation on the internet works. From your bank app to a login on some tiny startup. You just watched it happen, one step at a time. That is the whole thing. And now the connection is open, it is trusted, and it is private, which means we can finally send the thing we came here to send, the actual HTTP request. And what is inside that request, the get, the headers, what the server sends back, that is its own little world, and it is where you are headed next. So if you want to keep pulling this thread, stick around.